Do, 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 do. All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for the students and this class, and just ask you to be glorify what we do, that we all understand a little bit more about Lagrangian mechanics today, Lord. In your name I pray, Lord Jesus. Amen. So, so today I want to tell you guys about Lagrangian mechanics. So what this is about, basically here's the thing. We define L, which is a function of, let's say, Q sub I and Q sub I dot and possibly time t, all right? And so that's going to be equal to the kinetic energy minus the potential energy. So here, Q1 through Qn and Q1 dot through Qn dot, these are generalized coordinates, and their velocities. All right. So the Lagrangian is defined in terms of, like, physically speaking, you have a system, you can describe it with these n generalized coordinates. Now, let me keep it. This is the generality, but let's bring it back down to earth for a second here. So, like, typically, usually, think about a couple particles, maybe one or two particles. Let's start with one particle, right, with coordinate x, y, and z, and corresponding velocities x dot, y dot, z dot, all right? So then, in this context, the kinetic energy is just 1/2 mv squared, right? 1/2 mv squared, but that is exactly, 1/2 m. How do you write the speed squared in terms of the velocities?
Sum of the squares of partial velocities.
Yes. So x dot squared plus y dot squared plus z dot squared, right? So there's your handy dandy kinetic energy, right? And, well, the potential energy, that depends on the physics of the situation, right? Like, could be a lot of different things. So this is kinetic energy. And this is potential energy. All right. So let's see here. For example 1, we could let U of x, y, z be the potential energy, right? For the net force. All right, so if it's the net force, remember how this works? We have the net force vector is equal to minus the gradient of the potential energy function, right? That's how potential energy is defined. Its relation to the net force is that. As I'm dragging my Physics 231 class to accept at the moment, kicking and screaming through Calculus 3 that they shouldn't have to learn. It's not a prerequisite. I don't know, they're not all like that. It's just the ones that are. do I talk about, I mean, is there always a back reaction to trying to get people to learn things? Yes, always. It's not in the book. The book is dumb. So sorry. But let's see here. So this is the net force being that, right? And so I just want to set the stage here. What is, if we're talking about one particle, that's the net force. What are Newton's equations? Newton's second law says what?
Force and acceleration. Force and mass.
Yeah, the force is equal to the mass times the acceleration, right? So here, that translates into, or if you like, it's the mass times dv dt, right? Which I would rather write as ddt of the mass times the velocity, which is, by the way, the momentum. Time rate change of the momentum. So it turns out that the time rate change of momentum is going to be equal to, this gradient of the potential energy functions, right? Oh well. So these are Newton's equations, maybe not how you're used to seeing them, right? But that's what they are. So Lagrangian mechanics, for this particular example, the Lagrangian is equal to t minus u, which in my current context is 1/2 x dot squared plus y dot squared plus z dot squared minus u, which is, generically speaking, a function of x, y, and z. All right? So the Euler-Lagrange equations follow from what's called the action. So there's something called Hamilton's action principle. So Hamilton's action, I'm stating it wrong. Hamilton's principle of least action. All right, so we look at J of like Qi and Qi dot, whatever. Let me just say J of Qi is equal to the integral of the Lagrangian over time. Hamilton's principle of least action says that you form the action by the integral of the Lagrangian, and then it says that the equations of motion which govern physical motion appear as places where this action is minimized. This is Hamilton's principle of least action, but we already talked about last week how to minimize such an action using a variational derivative. It gives us the Euler-Lagrange equations. So if you had this many, so like in this one, I'm taking a step out of my example for a second here, guys, but this would give us, partial L, partial Qi is equal to ddt of partial L, partial Qi dot. I want to make those J's. I feel like a J is a better index. There we go. So you get as many sets of Euler-Lagrange equations as you have generalized coordinates, all right? But let me get back to my example. So what is the Euler-Lagrange? So here, how many Euler-Lagrange equations do we get for my example? Yeah, 3, right? 3, because we've got x coordinate, y coordinate, z coordinate. So let's write them down. So we have partial L, partial x is ddt of partial L, partial x dot. Partial L, partial y is equal to ddt of partial L, partial y dot. Partial L, partial z ddt of partial L partial z dot. And so like this, well, I'm not, let me just put an implication here. I wanted to work on both sides. So partial L partial x, how does that work? There is no spatial dependence to the kinetic energy, right? The kinetic energy here only depends on the velocities. So basically, we get minus partial u partial x equals to ddt of what? What is partial L partial x dot? See how it works? We get a 2 x dot cancels the half. We're just left with mx dot. In this, I get minus partial u partial y. Whoa. ddt, sorry about that. My dot, I probably should. That's right. We had important business to take care of there. So, all right. Let's get that one. Minus partial u partial z ddt of mz dot. But what is this? What is mx dot? It's nothing more than the x component of the momentum. So what we're looking at here is dpx dt, dpy dt, dpz dt. In other words, you take this collectively, it's nothing more than minus the gradient of the potential energy equals to dB dt. So the Euler-Lagrange equations reproduce Newton's equations as they ought to. And I decided to do this derivation for an arbitrary potential energy because it's the same trouble as if I gave us a formula, right? Yeah? No? Question? So, example 2. What if we had, let us say, thinking about a mass with x equals to r cosine theta, y equals to r sine theta, and let me just make a picture here, over here, I guess. So that was supposed to be a sun. It does look like an eyeball, my bad. So here's theta, and we'll say that, you know, x, y, r, so x squared plus y squared equals to r squared. It turns out that motion of a planet ends up being in some orbital plane as it happens. So it's not unreasonable to suppose that we can put coordinates in a plane to describe the motion of like a planet or something. So we're going to put, so that's the mass of the planet. So like the force of gravity here is something like minus g little m big M divided by r squared r hat. All right. And so this is going to be like minus partial u partial r r hat, if you think about it, and sort through the gradient stuff. So my point to you is just that the potential energy here, due to gravity, which is the only one to think about, I think it's just going to be minus gmm over r. If I take the derivative of this, I get a minus a minus, which gives me a gmm over r squared. But then by the definition of like potential energy, I put a minus on that derivative to get back the force, which should be attractive like that. And there's no theta component because the gravity just acts in like the directly radial way. So to finish my picture, this is M, and this is like big M, which is the sun. Maybe I should draw it like this. Sun. Top down. All right. So, okay, great. Well, that's the potential energy here. Obviously, I don't want to use x and y coordinates this time, right? I want to use r theta coordinates. How do I find the speed in r theta? How about this? We just take this, we differentiate, right? X dot is what? X dot is equal to r dot cosine theta minus r sine theta, theta dot. And here, y dot is equal to r dot sine theta plus r cosine theta, theta dot. So what happens here if we calculate x dot squared plus y dot squared? What do you get? Foil those out, see what happens. You might be like, but there's more than what you wrote down. That's true, but the other stuff, it'd be canceling. I'm gonna put that on a shirt. I'm thinking. Maybe over spring break I can start my merchandising. That's where the money is in the merch, right? Oh, that's weird. Okay, so there is the speed in polar coordinates. So maybe you can recognize this. It's the radial velocity squared plus the tangential velocity squared. Because this is r omega, like Vt is r omega. Anyway, so let's write down the Lagrangian then. So the Lagrangian is 1/2 m r dot squared plus r squared theta dot squared. And then minus u, which is actually plus g m big M over r. So there's my Lagrangian to describe gravitational attraction of two masses in the plane, assuming that the larger mass is at the center. And it's much more massive, so it's not moving, right? So this is kind of like the infinite mass limit of the sun. It's a lie. The sun actually moves, right? But dude, this is, the lazy thing to do. So my coordinates here are r and theta. So now I can write down the Euler-Lagrange equations. So for r, I have partial L, partial r is d dt of partial L, partial r dot. And I also have partial L, partial theta is d dt of partial L, partial theta dot. So what does that give me here? It gives me minus gmm over r squared. And that's equal to mr double dot. So that partial L, partial, let me write it out. ddt of mr dot, right? What is, so that we're looking at right now, is just the radial component of Newton's equations. It says that the acceleration in the radial direction is proportional to the force of gravity. And it acts to decrease the radius. Make sense? That's why the minus is there. What's the next equation? Partial L partial theta, what's that? There's no theta dependence here, is there? So partial L partial theta is equal to 0. All right? And that's equal to ddt of what? If we take the partial derivative of L with respect to theta dot, we get a 2, canceling the half, I get an m r squared theta dot. Do you know what that is? Anybody?
2 m r theta dot r dot plus m r squared theta dot dot.
Oh, yeah, you could differentiate this, but that would ruin the magic. This is apparently a conserved quantity, right? Angular momentum is right. So L is mr squared theta dot, also known as I omega. Right? I, the moment of inertia, is mr squared for a point mass. Yeah? That is, in fact, the moment of inertia times omega. That's angular momentum. So angular momentum is constant, right? Angular momentum is a so-called constant of the motion. Angular momentum is conserved by the central force, whatever that is. And, yeah. So there's a larger lesson to learn here, which is that when we partial differentiate the Lagrangian with respect to the coordinate, it's giving us momentum. See this? Like partial L, partial r dot, is the r momentum. Partial L, partial theta dot, is the momentum in the theta direction. But it's not a linear momentum, right? It's actually an angular momentum. So Lagrangian mechanics puts linear momentum and angular momentum in the same breadth, in the same formalism. We can treat linear coordinates and angular coordinates alongside each other with the same formalism. Yeah.
So if you solved the minus gm and r squared equals dm r dot, that would give you the for responsive. You just put a particle there and what path would follow?
Mm-hmm. Yeah. If you study this, you can derive that the motion has to be in an ellipse, which is characterized by, well, not necessarily ellipse, but the motion is a conic section, which you can characterize by the eccentricity, which is either, going to give you a hyperbolic motion, or a parabolic motion, or an elliptical motion, depending on whether it's bound or unbound by the energy that it has. Right? If it has sufficient energy, it's going to have parabolic. Well, parabolic's right on the edge. Hyperbolic means that it's not bound to the solar system, right? Elliptical orbits, they stay bound. But all of them conserve angular momentum. As long as we're just talking about gravity, there's not some other whatever. But yeah. So here's the thing. If I wanted to talk about two particles in three-dimensional space, then I would have 6 degrees of freedom. I have 6 generalized coordinates, and so forth. So like, if I had n particles, like not n, but I've used m for something else. Suppose I had k particles, then I would have n equals to 3k generalized coordinates, And I could use Cartesian variables to set up the equations, right? But maybe there's a more natural system of equation, the more natural choice of variables for some other problem. Like you could be talking about, like the double pendulum problem might be natural to describe in terms of, like the angular coordinates of a robot arm or something. See if I can draw that. let's see here. Ah. See if I can draw the picture. If we have, here's like the ceiling or whatever, and then we've got a mass, right, like this, and this is the angle off the vertical. Suppose this length is L, right? We can write the Lagrangian for this simple pendulum. So if I call the coordinates here, right, x, y, then that would be a lot like L, how's it go? L sine theta, right? L cosine theta, I think. But I guess I should put minus on this one, right? So what's the kinetic energy here? So I may not use capital L. That's kind of a dumb move. Duh. It's like I was using U for this the domain of the vector field in physics this week. And at some point it hit me, oh, U is potential energy. Oops. So I had to cross out U's and replace them with S for space in physics this week. But yeah, what's that? Just make it a vector. No, that I can't do. In either context, for the space or for the, I could have put a tilde on it though. That's what I should have done. Okay. So anyway, here's the Lagrangian: 1/2 m x dot squared plus y dot squared, right? Minus mgy. That would be the Lagrangian, the potential energy here due to gravity, just mgh, right? So here I'm then putting potential energy equal to 0 right here, right? You can do that. You can make potential energy 0 wherever you want. But this is probably not the greatest choice of coordinates, right? I can do better, right? This is 1/2 m what?
L times cosine theta plus sine. Cosine squared theta plus sine squared theta.
Yeah, x dot is what? I'm sorry, Shane, what were you just saying?
Just cosine squared theta plus sine squared theta.
So were you...
Times theta dot.
Right, so if I square those, what happens? You tell me it was m what?
L squared theta dot squared.
L squared theta dot squared, yeah. And you can kind of, like once you get into physics, you don't have to keep going through these chain rules. At some point you start to understand geometrically, if you think about like a little arc length being subtended here, right? The ds is what? It's just L d theta, right? So once you understand that, V is just ds dt, right? And so that's, ds d theta dt, which is, of course, L theta dot, So when you square it, you get L squared theta dot squared. I always felt like it was more proper when I did the chain rule on coordinate stuff, but you can derive these things less arduously simply by using basic geometric reasoning. So, and then of course I've got my minus mgy, which is what? Y is L cosine theta. So I plus mgl cosine theta. So here, there's just one coordinate, the theta coordinate, right? So my other Lagrange equation, partial L partial theta d dt partial L partial theta dot. Well, what is it? Well, it's this time it's interesting, right? Partial L partial theta is actually something. It's minus what? Minus mgl sine theta, yeah? From this piece. And what's the partial L partial theta dot? I think that works out to d dt of what? M L squared theta dot, right? In other words, L times dl dt, actually. I'm writing that way just to point out to you that this is the torque equation. What we're looking at is the torque. Oh, maybe do I need the L? Maybe I don't need the L. I think, is that just dl dt? Yeah, it's just dl dt. My bad. I think that makes sense, though, right? Because if you think about it, the part of gravity which is acting like this is the, I believe, the g sine theta term. And so you've got like mg sine theta is the force of gravity. And it's applied distance L from the pivot, so that it gives you that torque. Well, the torque is equal to the time rate change of angular momentum. So this time, or the Lagrange equation is giving us like the torque angular momentum equation we see in physics 1 as well. And there you go. That's the equation that governs a simple pendulum, which can't be solved, like you can only solve it approximately for small angles, right? Because it's kind of nasty, right? Sine theta equals to theta double dot. I don't think I can solve that exactly, yeah.
Why is there a time dependence on potential energy?
Well, the time dependence in potential energy, it's wrapped up in the time dependence of theta.
So is that add a sine theta to your ML squared theta dot?
Well, that's a derivative. I mean, this could be simplified to ml squared theta double dot if you wanted. So, so that would give us theta double dot plus g over L. The m's be canceling. Sine theta is equal to 0, which in the small angle approximation gives you theta double dot plus g over L theta equals to 0. We write down the characteristic equation. If you know this sort of thing, my frequency here is, the square root of g over L. And so my solution for small angles is something like theta naught sine of the square root of g over L t plus some sort of phase angle, whatever. But this is not an exact solution to the problem. This is a solution that's only valid for small angles, right? Like sine theta is equal to theta within a percent if we're like less than 20 degrees. Otherwise, this is a nonlinear second order differential equation. I don't know how to solve it in general. So this is approximation, all right?
The dl dt would have to have that dl sine theta.
The what?
The dl dt of
The dl dt. Well, I'm not sure what I'm not hearing it yet. I'm sorry.
where you say d dt ml squared theta dot is dl dt.
Yeah.
Wouldn't dl dt come out of the term on the second term?
Well, why would it have a second term? I'm not seeing it. But it's partial L partial theta dot. Are you saying there should be something from this, from the partial L partial theta dot? I mean, we calculate partial L partial theta dot. I mean, the thing inside the brackets is L. That is also true. I'm sorry, I'm using, oh, curses. So angular moment, I'm sorry, I see the confusion. I'm talking past my, I'm just trying to use L in two different ways in the same equation. What's the problem? Why can't you understand? But, so sorry.
That L on the left below it is also Lagrangian?
No, this is the Lagrangian.
Oh,
Yeah. So this is T.
You almost get it the third time too with that pendulum.
So there is another way to do this problem using the method of Lagrange multipliers for the Lagrangian. And so the way that's done is to not, it's a little bit, this is kind of a silly use of it, but it just illustrates the idea, which is an incredibly flexible idea. So what's passed here, Preston, is we're going to solve the central force problem. We're going to not assume that the mass is fixed in place after you leave. Cool. So if we look at L, let me call it L2, we can do 1/2 m r dot squared plus r squared theta dot squared. Plus mgl cosine theta. Oh, I shouldn't do L. I should mgr cosine theta. So here's the difference. I am not assuming. Basically, what's happening here, if you could think about this as an r theta problem where r has been frozen out. Right, to describe the pendulum motion, I'm still thinking x equals to, well, I guess I'm not thinking. I'm thinking x equals to rats. It's almost. I'm sorry. It's a little bit of a twist here, isn't it? But it's the idea remains the same. The sign doesn't change anything here, okay, guys? Like if I put x equal to that and y equals to that, it's still the case when you calculate the x dot squared plus y dot squared. You'll still get this, right? Even though technically speaking, this is non-standard polar coordinates. Okay. I hope you're not too bothered by this, because I really don't want to work through it again. So here's the ingenious thing that's really bizarre. So like, what we're doing is we're putting r equals to L. So here's how the method of Lagrange multipliers looks like. For this, you do minus, or no, plus, I can't remember, plus I think, plus lambda. And then you just put the equation, basically something that's 0, subject to your constraint. So my constraint is simply r minus L. That being 0, right, gives us back the simple pendulum. And so the deal is that now we have partial L, partial R is d dt, partial L, partial R dot, partial L, partial theta equals d dt, partial L, partial theta dot, and partial L, partial lambda equals to d dt, partial L, partial lambda dot. This is how the method of Lagrange multipliers generalizes to Lagrangian mechanics. You just add lambda times your constraint. And when you do that, the constraint equation becomes one of the Euler-Lagrange equations. See what happens with my partial L, partial lambda? Like, just focus your attention here. What happens with this? 0, 0, 0, 0, 0, 0, 0, just this, r minus lambda, r minus L rather, little l, on that side, equals to what? And that, if you take that, right, and these are, I don't even, I mean, this is going to give you mr theta dot squared equals to ddt of mr dot, and this gives me minus mgr sine theta equals ddt of mr squared theta dot. So when you put, I think I might have lost a, I might have done, I think I did something wrong. What's partial L partial R? It's not just this, is it? What else is there? There's more here, isn't there? That's just what comes from this piece. But there's also this one and that one, right? So I also have plus mg cosine theta and also plus lambda, right? So so you get R equals to L, which means that R dot is equal to 0, right? So then, if you look at this equation down here, right, it gives us, let me write it up here. It gives us that lambda is minus mg cosine theta minus ml theta dot squared. And then that one, it gives me the minus mgl sine theta equal to ddt of ml squared theta dot, right? We have R equals to L from this equation here, so I'm putting that in. I'm plugging that into these equations. At this point, I think we're back to where we started, right? Because we had minus mgl sine theta equals to the time derivative of ml squared theta dot, right? But we also get this equation, which is that lambda is equal to minus mg cosine theta minus ml theta dot squared. What is this? You might not recognize it, but this is the formula for the tension that's needed to keep the mass moving in a circular arc. The meaning of the Lagrange multiplier is it's the force that's needed to maintain the constraint in the motion. So like the method of Lagrange multipliers for Lagrangian mechanics is actually pretty deep and interesting. It has a lot to say. It's a little bit more interesting, I think, than the method of Lagrange multipliers that we know from Calculus 3. I remember when I took classical mechanics, my professor was like, he was just awed by this method because essentially it just comes from adding 0 to the Lagrangian. He thought it was a great mystery that just adding 0 to the Lagrangian could reveal so many mysteries, just like this. This becomes more impressive if you do stuff like, suppose you've got a bead rolling on like a bowl. You can write down like the equations of motion for that in terms of the coordinates of the bead. Basically, you've just got gravity, which is minus mgz, or mgz for potential energy, and put like spherical coordinates on the bowl. The Lagrange multiplier equation just becomes that the spherical radius is equal to the radius of the bowl, and that will like derive for you the necessary force to keep the thing on the bowl and stuff like that. But anyway, enough about that. Let me spend the rest of the class time on a famous problem in physics. This is the problem of central force, the central force. What is a central force? I thought I already had it out. Where did it go to? Man. No, this is... thing is, I just opened the thing. I don't understand why it's not open. I am confused. You too? That seemed unnecessary. Let's see here. So I've got it posted here, central force problem. I wanted to make it bigger. Oh, okay. So I put it in advanced calculus. So no, this is after Kepler, considerably after Kepler, because what I'm about to show you is something that was derived using Lagrangian mechanics. So I think this is, I don't know if it was Lagrange himself or like some other significant 19th century physicist. I'm not sure who did this first, but what I'm about to show you is the solution to the two-body problem in the context of central force motion. So the idea here is simply that we have two masses which are acting on one another by a force which is controlled. It's in the direction in which the masses are connected, and the magnitude of the force only depends on the distance between the masses. So this is called a central force. In my junior level physics class, we spent about a week going through what I'm about to show you. If I could ever find it. Seriously? What is this garbage? I swear. There it is. Ha. At least at the moment, Liberty IT has no way of getting their hands on my actual hard drive. So it's safe. It was a fake download. It looked like it downloaded, but it didn't really. So this is the central force problem. We have two masses, mass 1 and mass 2, all right? The one is at position 1, the other is at position 2. We assume the existence of an inertial frame of reference for which we can measure both of these positions. So this is XY coordinate system is a fixed inertial frame, somehow existing, perhaps with the fixed stars in the background or whatever. So what you do is you introduce the center of mass. The center of mass is the, well, I would say this is the weighted average, but I've only divided by mass. So, sorry, that's a stupid joke, but so M1R1 plus M2R2 divided by the mass, right? So the bigger the mass, the more weight it gets. And so the force only depends on the distance between these masses, which is R2 minus R1. We'll define the relative position to be R2 minus R1, R. Now, that gives us these coordinate transformations. We have R is equal to R2 minus R1, and we have the center of mass, big R, is equal to this plus this. Now, these equations you can solve. You can invert them to get that R1 is equal to this and R2 is equal to that in terms of the center of mass and the relative coordinate, R. And what's interesting then is, of course, you can calculate the speed with respect to the center of mass and the relative velocity. So I differentiate this and that to get those relations. So this is the velocity of the center of mass, the relative velocity, and those are related to the velocities of the first and second particles according to calculus, like so, which gives me this formula and that formula. But then we can calculate the Lagrangian with respect to either coordinate system. You see, we could either calculate the Lagrangian with respect to the initial Cartesian coordinate system, x, y, or we could use these center of mass and relative velocities. So I trade my v1.v1 and my v2.v2, right? So this is kinetic energy for the first particle, kinetic energy for the second particle. I trade that for this and that. And it turns out that you can calculate these dot products and you get this. So it turns out you have no cross term. You just have like the center of mass velocity squared with an effective mass of the sum of the two masses, all right? So this describes the collective motion of both masses. And then this other piece, which describes the kinetic energy having to do with the relative motion of the two masses. And so we have this quantity here, which has dimensions of mass. So we call this an effective mass. This plays the role. Like if you look at this, in the case that M2 was way, way bigger than M1, what happens here? If M2 is way, way bigger than M1, then the denominator just becomes M2 squared, right? And this just simplifies to this term, right? M2 squared is bigger than M1, so this would just collapse down to M1 M2 squared divided by M2 squared, which would just be M1, right? So if M2 was way, way bigger than M1, then this would just simplify to M1, the relative velocity squared. Because if M2 is way, way bigger, it's just sitting somewhere. It's not moving a lot. M1's the one that's doing all the moving. Anyway, so that can be simplified, actually, like this by algebra. So there's a better formula for the reduced mass, all right? And so then we have the Lagrangian has 1/2 the total mass, the velocity of center mass squared, plus 1/2 the reduced mass times the relative velocity squared, minus the potential energy with respect to the relative distance, right? Because we're assuming that the force that binds these two things together or pushes them apart, it acts radially on the basis of the relative distance between the two, which we've called r, right? That's the magnitude of r2 minus 1. So, like I said, typical, I think I've, I switched the M2 and the M1 for my discussion. Sorry about that. So if M1 is the sun and M2 is the earth, then the relative mass just becomes the mass of the earth. Oh yeah, the smaller one. So, okay, anyway. And so typically I think of the center of mass as being where the sun is, right? Because most of the mass of the solar system is in the sun, right? The sun has a mass of like 2 times 10 to the 30th, whereas the earth mass is like 6 times 10 to the 24th or something, right? So the sun is something like 1,000,000 times more massive than the earth. And I don't think it gets much better for the other planets. I mean, well, some of the planets are bigger, right? But still, relatively speaking, the sun is like heavy. So anyway, so we have Euler-Lagrange equations for this problem, and we have like the 3 Euler-Lagrange equations with respect to the center of mass coordinates. Let's say x, big Y, big Z. And these are kind of boring equations. They just say that that we maintain constant rectilinear motion with respect to the center of mass. It just glides along, whatever it's doing, with respect to the fixed inertial frame. All of a sudden, we seem to have found a Z here. That's interesting. I'm not sure where that came from. Okay, I think the full story here is that if you start with a central force, you can do some calculus 3 style argumentation to prove that the torsion has to be identically 0. That follows from the fact that if the force is central, the cross product of the force with the radial vector must be 0, and as such, dl dt is 0, which is tantamount to saying that the binormal vector has to be constant. So these details have been left out of this particular diatribe, so that you could put z back in. I took it out to make it simpler. But this is, of course, true. I mean, we are in 3 dimensions. This problem is a 3-dimensional problem, but that's the motion of the center of mass, 3-dimensionally speaking. It just so happens with central force that the relative motion has to happen in a plane. With a central force, you can't have a genuinely 3-dimensional motion. Between 2 bodies, at least. Now, between 3 bodies, that's an open question, I think, exactly. The 3-body problem in general is not solved. We have specific solutions to the 3-body problem, but not the general 3-body problem. I don't think. Well, anyway. So this is my Lagrangian, right? I just talked about this part. Now we should talk about that part. Of course, what do you think we're going to do over here? Instead of sticking with x dot squared and y dot squared, we're going to trade that out for an r dot squared plus r squared theta dot squared. That's the better way to do that. As I do here, as we did already today. So these are the Euler-Lagrange equations for the relative, the relative distance between the masses and the angle. And so we get conservation of angular momentum, like this, and we get, this is the radial equation. All right. Mechanists call theta an ignorable coordinate because it's just constant, right? You can integrate it out. All right, so great. Now this is where it starts to perhaps get interesting. You can take the radial equation and you can rewrite it as such. Then you've got the reduced mass times the second derivative of r is equal to minus the the radial derivative of this business. And then if you take this equation and you multiply it by dr dt, you get this. All right, this is a common trick in classical mechanics. Multiply by a derivative in order to take an equation of motion and turn it into a conserved quantity. So this is a very sneaky trick. What we're doing is multiplying by the velocity in order to make all of these things into a time derivative. See, this is ddt of r dot squared. And this is, by chain rule, ddt of all that junk. So why would you do this? Well, this gives you something else, a new conserved quantity. A new conserved quantity, namely 1/2 mu r dot squared plus ur plus L squared over 2 mu r. This is what we call energy. The energy is 1/2 mu r dot squared plus this right here. And this is what we call an effective potential. It's as if this is a one-dimensional problem with this being the potential energy. All right, it's not a genuine potential energy. This is just rewriting of equations to make it look as such. But nevertheless, you can draw energy diagrams and understand the motion in terms of the usual analysis of energy in one-dimensional problems. And so just to recap, we have this and that are constants. They're conserved quantities for the central force problem. And we have these two relatively simple differential equations once we specify a choice of UR, right? I still haven't told you what the U of R is. Typically, I like to think about it being, minus GM M over R, like we started with, right? But it could be something else. These same equations would classically govern the motion of, attractive forces between molecules, as long as they're just binding the molecules in terms of the radial distance between them. This would still be holding if this was something other than gravity, if it had some kind of different potential. These equations still hold. Anyway, so we have these two equations, which then you can solve. So after a little bit more of tricky business, a little bit, this doesn't really matter to us so much. I'm going to just kind of go fast through it. You can trade the differential equation we had up here for actually a second order differential equation in the reciprocal of the radius as it happens. This thing is actually pretty easy to solve because it's just a constant coefficient second order differential equation in the reciprocal of the radius. So that you can solve using typical Math 334 stuff. This is the so-called orbit equation. You can solve the equation of orbit from this. And let's see here if I have any more. So in particular, for the case we're most interested in, which is Newton's universal law of gravitation, the orbit equation just becomes this right here, which is, this is just a constant. And so we're just solving that. And of course, this is easy to solve. It's u equals to u naught cosine of theta plus theta naught u of p, but u is 1 over r. So if we solve this for 1 over r, we get the equation of a conic section in polar coordinates, where this is the radial distance between the center of masses of the two objects, not from just a fixed origin. So this allows for both of the masses to be moving. This is actually allowing, this doesn't assume that the sun is fixed in one point in space. It's allowing the sun to do a little wobble at the same time the planet is doing its elliptical orbit. They both orbit, both the sun and the planet orbit around the center of mass of the sun-planet system. And that's the equation.